I'm not there again today. I am at home. My daughter is sick, and so I have to be here at home to take care of her. Let's just jump straight into things. We are a little bit behind schedule, and so we are going to move forward into some AP content. We did not finish the AP section for last section that we were working on, the rational expressions, but we are just going to leave that behind, and we're going to move forward onto the exponents and radicals AP, because that is a little bit closer to what we've been working on in class anyway. And working on this will actually be helpful because it's some radicals work, which is going to be coming up in our tests next Tuesday. So just a little outline on what's going to look today and Friday and Monday. Today and tomorrow we'll do some learning from the AP book. We'll probably do AP lesson 1 today, and I'm trying to decide if we might skip over AP lesson 2 and do AP lesson 3, just because it talks about imaginary numbers, which is actually very interesting, and I'd like you guys to see that. So that's sort of what it's looking like for this week, and on Monday we will do a little bit more review. I'll have a review package to print and give to us so that we can prepare for the test on Tuesday. All right, let's jump in. So, multiplying and dividing radicals. Here we're actually just starting off with something that we've already looked at a little bit before, as in when you're looking at a radical with a variable inside of it, the variable could be anything. So if it was something positive, like the square root of 2, then you are able to do that because you can square root positive numbers. But if you're trying to do a square root on something like a negative 2, then, well, you couldn't do that. So when we're talking about restrictions here, we're just saying what are the possible values that could go inside of the radical. And this first scenario, we would just state it as x is an element of the real numbers. Something kind of interesting happens if in the radicand it is already squared, because, well, in this instance, just imagine you were substituting negative 2 and then squaring it. You'd get something like the square root of positive 4, and then it would work. So in this case, x is an element of the real numbers, and I realize now that I made a mistake there. X is just greater than or equal to 0 in this first instance. The numbers have to be positive. They have to be bigger than 0. They have to be positive. So in this second scenario, that's the one where x is an element of the reals. And in this third one, you can take the cube root of positive or negative numbers. So this one, x is also an element of the reals. Just maybe to give you a concrete example on that one, you're allowed to do something like the cube root of negative 8. The result is negative 2. So what's a little bit new for us today is the fact that there are variables inside of the expressions, and because of that, we have to state restrictions regardless. If it happens at any point in our work, we have to state that there's a restriction and that variable cannot be a certain value. So let's try this out. Right away, I can state the restriction for this one. I have a variable inside of the radical, and it's index 2, so a has to be positive. The rest of this, converting to entire radicals, is not anything new per se. We're just going through this process, a cubed, but then I'm going to square root and square it, and then multiply by So three, that is a to the 6. We get 3a to the 7. And I should state my restriction here. Okay, I'll skip that one for just a moment because it has two variables, a and b, and we'll look at that in just a second. But let's take a look at this one next. I look at the root index first for the restrictions, and it's a cube, which automatically tells me that there are no restrictions on the variable at all. B just is an element of the reals. And I go through the work. Two cubed is 8. 8 times 4, 8, 16, 24, 32. B squared to the power of 3, that's b to the 6. And then add 2, b to the 8. And then the index remains 3. Add the restriction at the end. So I'll skip this one. That's one that you can do on your own. To the power 4, I guess the only thing I should mention here is just the restriction itself. Index is even. So it acts just like it's a root index 2, where this variable x has to be positive. And then you could do the work in just a moment. The restriction on this one is kind of interesting because you have two variables inside of the radical, and it's not necessarily the case that just a has to be positive or b has to be positive. You actually need a multiplied by b to be greater than or equal to 0. And that's all the detail that we really need on this one. We don't have to go case by case because that would be a little bit too much for us at the moment. So we can just say that the multiplication of the two variables, a and b, have to be positive, which means if a was negative and b was negative, that result would be possible. But that's all we have to have for that in this moment now. And then, of course, going through the work here, you just raise this to the power of 2 and square root it, so I'm just going to skip that. I'll actually just pause that for a moment. Actually, I'll ask that you pause this for a moment so that you can take just maybe 1 minute to work on this problem and this one and see what you get. Okay, moving on. We are going back to simplification, and I think the other day when we were working on the formative, many of us had remembered how to do it, but there was also a little bit of friction in remembering the process, and so this will be a good time to review that just a little bit. And then we will also tackle what's going to happen with these variables. How do we deal with those? First things first, though, if the root index is squared, you're going to be looking for perfect squares, perfect square factors. 12 can be divided by 4. 12 is 4 times 3. Now, I'm going to show it a little bit differently than before because I think it'll be somewhat useful to see how we're going to deal with the variables here. And it works like this. A to the power of 3 using our exponent rules, can be written as a squared multiplied by a to the 1. So this is useful because a squared is a perfect square, but a to the 1 is not a perfect square. A to the 3 then, I'm going to write a squared in this first radical, and a to the 1 in this radical at the back. And what I'm essentially doing is keeping all of our perfect square components or factors at the front inside of the radical here, and all of the remaining components in the second radical, which is not going to be able to simplify. It'll just be stuck as it is. So b to the power of 4, that is a perfect square because the exponent is divisible by 2, and that ensures that it's a perfect square. So, what's the square root of 4? 2. The square root of a squared and b to the 4. This cannot be simplified. And then I state my restriction. Honestly, for this one, yeah, the restrictions, honestly, anytime there's two variables, it's getting to be a little bit strange. So if I thought about that just for a moment, b to the power of 4 is going to be squared, so it's always going to be positive, which essentially just means that a would have to be greater than 0. And b could be anything. Yeah. I'll skip this one. You can try that in a moment. But let's look at root index of 3, just as a reminder and a refresher on how that works. You're looking for perfect cube roots, or factors that are perfect cubes. So 81, I believe, can be divided by, well, 27 probably. I'm just trying to get my calculator to work. And I'm just drawing a bit of a blank. Yes, 27 and 3. All right. And now, the only thing that's a little different here is the root index is 3. And so when I look at the variables and the exponents, I need to factor a so that one of the factors has exponents that are multiples of 3, and then the other factor is just the result. I can break a to the power 10 into a to the power 9 and a to the power 1. 27 times 3 is 81. A to the 9 times a to the 1 is a to the 10. And b to the 12 is already just good to go. Cube root of 27 is 3. A to the 9, no, a to the 3. And b to the 4. This one's kind of interesting. The variables a to the 10, b to the 12. So it doesn't matter what a or b are because it'll always be positive. And it wouldn't matter anyways because the root index is a cube root and you can have negatives inside regardless. So a element of the reals, b is an element of the reals. I apologize. I'm writing on this, it's a graphics tablet, and it's not bad, but it doesn't really have a screen, and so not always the most legible, but hopefully it's good enough. Let's say pause again for another minute or two so that you can work on these two problems on your own and work together if you're feeling a little bit stuck. And in just 2 minutes or 3 minutes, come back and we will keep going. Okay, let's keep things moving. Multiplying radicals. I'm going to go pretty quick here because we've already basically been working on this, and I've kind of been doing that work throughout the lesson anyways. How would we multiply these two factors together? You'd multiply the coefficients, and then you'd multiply the variables. So you'd end up with 12 x to the 3. And we've looked at multiplication on radicals, and we've been working on that already. So you can just factor a radical. The nth root of a times b is equal to the nth root of a multiplied by the nth root of b. So this is suggesting order of operations can be changed without having an impact, truly. So what is it going to look like when we're multiplying radicals together? Really quickly, I'll maybe use a highlighter sometimes just to keep things a little bit organized. Highlighting coefficients and highlighting radicands so that you can see a little more clearly that whatever's outside stays outside when you multiply, whatever's inside stays inside when you multiply, and the result here would be 15, and then the root would be 20 times 6, 120. Completely simplify. This is not fully simplified because I can absolutely take out some perfect square that is 120. If you're not quite sure, I'd probably start with 120 divided by 4, but I don't think that's going to be large enough, and it actually is because the result is 30, and that works out. So 4 times 30, which gives me the square root on 4 is 2 times 15. Kind of a strange result, but it is. 15 is stuck, or sorry, 30 is stuck because 30 is 15 times 2, and 15 is 5 times 3. So 5 times 3 times 2, none of those values are perfect squares themselves. So the radical, root 30, cannot be simplified any further, and you're just good to go on that one. Now, this one is honestly a good one to just talk about for a moment because we're going to see this happen pretty soon in the problems that are just below this. Anytime you take a radical and multiply it by itself, you will just end up with the radicand. The reason being 13 times 13 is 169. And you can do the square root on 169. I could even write it this way. The square root of 13 squared is 13. So it's sort of like the radical cancels out. Not maybe the best way to say it, but that is in essence what is happening. So I want to jump to I guess I don't want to jump too far forward. I'll use a highlighter just to keep the outside coefficients and the radicands separate. And now when I multiply -2 cube root 12 multiplies with the first term, I get -8 cube root 24 and +6, add 6, cube root 36. And then we try to simplify. Trying to do a bit more of this in our head now. 24 is 8 times 3. 8 is a cube root, which is 2. And 36, is that divisible by 8? No, not by 27. So 36, cube root 36 is just stuck as it is. I end up with -16 . Now, it's at this point that I should probably just mention or highlight adding and subtracting radicals. This is the AP lesson 2, but it's fine to mention a bit here. If I actually wanted to add the coefficients, -16 and 6, the radicals themselves would have to be identical. The root index and the radicand would have to be just exactly the same, but they are very different. So this is how the expression is simplified, and it doesn't look great, but that is just where we have to leave it. Okay, let's look at one more here. I won't highlight just for the sake of some time. We get 16 and shortcut a little bit, multiplying the root 5s. Now we get 8 root 5 and -8 root 5. -4. $80. And the thing to sort of note on this one is you add 8 root 5 and subtract 8 root 5, that becomes 0. It essentially disappears. So 80 subtracted by 4. And you end up with 76. I've mentioned this before, but these factors multiply together. These factors are called conjugates. And when you multiply by conjugates, interesting things happen, actually really useful things happen, like radicals will disappear. And that is another thing that I will show you in just a moment that is useful to use as a tool to fix certain problems that we will see. So I'll ask you to pause again. See, I know these ones look a little bit tricky and complicated, but see what you can do on these next two. I'll probably give you about 3 minutes or so to try those ones, and then we'll keep moving forwards. Of course, work together if you need to, and we'll start up again in just a moment. Okay. So, dividing radicals and rationalizing denominator. Dividing radicals is going to work exactly like you'd expect, kind of like multiplying. In order to divide radicals, we divide the, I'm going to use layman's term here, we divide the outside with the outside and the inside with the inside. And we can always verify our answer by using our calculator. Yeah. And we always want the radicand to be as simple as possible by the end. So, essentially it works like this. 10 and 2. If you wanted to rewrite it, you could look at 10 and 2 inside as a radicand, and then 10 divided by 2 before you do anything else, and you just get root 5. But you don't have to go through that step of showing it. You can actually just perform the operation itself and the simplification. So 12/18, 6 12/18, I get 2/3. And 60 divided by 5 should give me 12. Before you move on, you just double check and make sure that your radicand is simplified, and it's not. So I have to go 4 times 3, square root of 4 is 2. I get 4 root 3 over 3. Oop. Don't be fooled by the radical 3 and this whole number denominator 3. Those cannot be simplified because this one is a radicand and 3 is not. So we cannot divide those pieces. They must both be radicand if we want to divide. And this one, I'm highlighting those radicands. I am going to do a bit of fraction work just to make this a little bit more obvious what's happening, but you'd look at it as 2 root 18 subtracted by So if you use your fraction rules of adding and subtracting, you can actually separate the fraction into 2 terms completely, and then you can simplify each term separately. Choose divide into 1, 6, 12, 18. I just get root 6 on this first term, root 8. Three times 2 is 6. That was a 4 times 2. The 4 left, and I was left with a 2. Okay. Now, the last rule that we have to look at before I can just leave you some for some practice is that we would call this not simplified as an expression, because the radical, the root 7, there is a radical on the denominator, and we are not allowed to leave radicals on the denominator. The process is going to be called rationalizing the denominator, because we want the denominator to become a rational value. And this is what it'll look like. In blue here, don't write this just yet, but it's our awesome math trick of multiply by 1. But not just any one, not the number 1 itself. It has to be a little bit more fancy, a little more interesting than that. We will multiply by root 7 divided by root 7. That is equivalent to 1. But what actually happens when I perform this multiplication? The denominator, root 7, I end up with root 49. But the root of 49 is just 7 itself. And take just one moment in your calculator, type in, evaluate as a decimal what is 1 divided by root 7, and evaluate what is root 7 over 7, just to really convince yourself that they're the same. You should get something like 0.37. All right. So let's try again. We will multiply by what we see on the denominator. Now, for this one, we want to be a little strategic. It's going to be simpler if we just multiply by the radical itself. We don't actually have to include that 5. It's irrelevant when we're rationalizing the denominator. We just have to multiply by the cube root of 4. But you'll see here that wouldn't quite be enough, right? Because 4 times 4 would give me 4 squared. And I can't cube root 4 squared. So I'm actually have to multiply by the cube root of 4 squared, because this is the result. Four times 4 squared . 5 times 4. So when you're rationalizing a denominator that has a root index 3, just be a little bit more careful to make sure that you actually create a radical that is a perfect root. A cube root in this case. 4 cubed is a perfect cube, and you can cube root the 4 cubed. And the most interesting one is this here, 2 minus the square root 3. Just before I say it, think to yourself for a moment, what would you multiply by this? Like, what would you multiply by? It's still going to be my sneaky 1, sneakily. But what is it going to be? And it's a little trickier because that is a 2 terms on the bottom, and that looks a bit different. But kind of giving it away now, it being 2 terms maybe will ring a bell, as conjugates are probably going to be useful here. And this will solve our problem completely. I don't want to do too many shortcuts because shortcuts can be dangerous when we're just learning that skill. So multiply the numerator first, 4 plus 2 root 3. Now I won't shortcut. I get 4 plus 2 root 3 minus 2 root 3 minus root 9. So I just end up with 4 plus 2 root 3. And again, just because I find the result is sometimes strange when you compare it to your original expression, to convince yourself that you've done the work right, and actually to check your work that you've done it right, you should put it in your calculator just to see the decimal approximation. 4 plus 2 root 3 is that equivalent to this expression here. And once you've decided that they are, you can move forward and you're good to go. So let's do these pretty quick, and then you'll be on to the practice on your own. When we jump into these ones, I just want to remind us that we now have there are two ways that we're dividing radicals. We can divide if it's friendly, like 24 can be divided by 3. That does work. But if it can't, then in order to simplify the expression here, we have to rationalize the denominator. So always look for that division rule first because it's a little bit simpler. But you'll see most of these, you can't use the division rule. You're actually simplifying by rationalizing the denominator. So let's just go through those pretty quick. I'd get root 8x and 8 now. Restrictions. You always have to take the most restrictive restriction. So if I look at this one, there is no restrictions because that becomes positive. When I look in the denominator, x has to be positive. Well, greater than or equal to 0, but it is on a denominator. So it actually cannot be 0 because 3 times 0, the root of 0, this entire denominator would be 0, but you cannot divide by 0. A fraction cannot have 0 as a denominator. So my restriction is x has to be bigger than 0 without the greater than symbol. Strictly bigger than 0. Here we rationalize the denominator. For root 10n all over 3 times 2. N has to be bigger than or equal to 0. This next one, we're just practicing rationalizing when the index is a cube. So we're multiplying by our sneaky 1. Cube root of 6 squared. Ooh, 11 times 6 times 6, 390. Y times 6, which gives me 2 over 3y. And then the radicand 396, factorized, it is 11 times 2 times 2 times 3 times 3. So there is no perfect cube that can come out of that. So that is completely simplified as a radical. Restriction on the variable. We actually still have to state the restriction on the variable. It is just y cannot be 0 because the denominator. And I just want to mention too, Microsoft Word, not always the most friendly when it comes to radicals and exponents, because when you look at this, it sort of looks like y cubed instead of y multiplied by cube root 6. So just be really careful. Yeah, be really careful with that root index just before you start a problem. Make sure you understand if it's the value that is the root index or if it's actually an exponent on the variable itself. So yeah, just be careful. Here, maybe I'll skip that one because we've already done the rationalizing the denominator. But we'll do this last one together, and then I'll just give you some time to practice for the rest of class. Okay, this looks kind of complicated, but it's not going to be too bad, I think. We have two terms on the denominator, so I will have to rationalize. I'm not even considering if we could do simplification of division because we just can't because of two terms. If there are two terms in the denominator, it's going to have to be rationalizing. Multiply by the conjugate. I am going to zoom in a bit for this one. High probability that I'm getting sick from my daughter. Full disclosure, my wife picked up my daughter yesterday and she sneezed directly into my wife's mouth. So that was funny, and definitely she's getting sick, so I'm sure I'll be getting sick shortly. But I'm expecting to be back tomorrow. But let's hope for the best. Okay, let's multiply this. It's going to be slightly a nightmare, but we'll do it. Let's use a bit of shortcut on the denominator because if we don't, it's going to be terrible. 5x cubed, and then minus 4 times 2. Okay, that's not so bad. And then on the numerator, it will be kind of terrible. 10x to the 4. And then 6 minus 2 minus 4. Okay. Let's clean this up a bit. 3x squared plus 12 minus 10x Let's look at that for a moment, make sure I didn't make any mistakes. Yep, I think we're good. And I also believe that is completely simplified. Because we have to be a little careful. The radical root 10 in both of this scenario. 3x squared root 10 minus 4 root 10. Definitely the root 10 is identical as the radical, but it goes and it defaults now to just polynomial rules. 3x squared minus 4 cannot be simplified. You can't collect any like terms there. It's just 3x squared minus 4. So there is no real simplification in that case. For the same reason here. Yes, the radical is identical, but the coefficients using polynomial rules are not. So that is as simplified as that expression can get. In terms of restrictions, though, We have a square root. Oh, you know what? We kind of should consider this denominator, but that is seeming a bit too complicated for us right now. The only thing I'd consider is just that x has to be positive. That's the only thing I'd really want us to say. Greater than or equal to 0. Yeah. Yep. If you really want to stretch your mind a little bit, consider this statement. Make sure that that's not equal to 0. Not beyond our scope, but just a little bit more math than I'd expect us to do at the moment. So think on that if you want to. And if not, and you want to save yourself some misery, then just go for it and jump into some of that AP practice. I hope today this worked okay for you all, and do your best. I know some of these can be probably a little bit tricky, but it's good practice anyways because it's dealing a lot with radicals. And the more we just practice those radicals, the less we have to worry about it for Tuesday when it comes to our summative. So thank you very much. I appreciate all of you guys, and good luck with your practice.